So hello, welcome, and thank you for joining us for this Prism Sound Wednesday webinar. I'm glad you could attend, and I hope you find the content interesting and engaging. Today we're going to be talking about measurements on audio power amplifiers, and we're going to do things a little bit differently to perhaps how we sometimes run our webinars. Today we're going to be focusing very much on the practical side of our measurements. We're going to be diving into the details of our tests, looking at what the results mean, and getting to grips with some of the problems and pitfalls you might encounter when you're trying to make measurements on your audio power amplifiers. So, just a brief introduction to me. I am your presenter here today. My name is Simon Woolard, and for those of you that don't know me, I'm an applications engineer here at Prism Sound headquarters in the UK. And for those of you less familiar with Prism Sound, the company, we are a manufacturer of, amongst other things, a range of professional audio test and measurement systems covering analysis of both analog and digital audio signals over a wide range of potential devices. So I'm going to be talking you through the presentation, and we're going to be using some of the Prism Sound measurement solutions to help us illustrate our demonstrations and practical measurements during the discussion. So what will we be covering today then? Well, this is our agenda in brief. First of all, we're going to take a look at that dreaded scenario. You've made some measurements on your audio power amplifier and something, or some things in the plural, don't look right. So we'll take a look at that first of all, and that will set the scene for the rest of our presentation, where we're going to do some debugging on those initial measurements, taking a look at what went wrong, and ultimately answering the question why those measurements didn't look right, and hopefully we will be putting them right. So that will lead us on to a discussion of the measurements that we've covered in that first section. We're going to have a look at some single tones in our practical workshop. We're going to have a look at some sweeps in our practical workshop. And we're going to take a look at some maximum output power measurements of our amplifier. And then, importantly, last but not least, we're going to take a look at how you avoid blowing things up on your test bench, either the device under test or the measurement system itself. So that's what we're going to aim to get through today, and I will start off by taking a look at this dreaded scenario that I mentioned. My measurements don't look right. So let me first introduce you to the test and measurement system that we will be using here today. And I know some of you are using this system already, others of you may be less familiar. This is one of the systems in the Prism Sound range called the D-Scope Series 3. This particular solution has analog outputs, analog inputs, digital outputs and digital inputs, and it's one of the options that we provide as part of our range. Today I'm just going to be focusing on analog measurements. I'm going to be taking the analog outputs of my test system into the line level input terminals of my power amplifier, my device under test, and the outputs will be connected across some resistive dummy loads, which is where I'll be measuring the output voltages and distortion and power and all sorts of other things that we'll take a look at very shortly. Now, this will be unfamiliar to most of you. This is something that I'll be using for my practical workshop today. It's a new application for the D-Scope Series 3 system called AutoSequence. What is this? Well, it's designed to make your life easy if you want to set up sequences of tests for a power amplifier or a D2A converter or whatever else you might be testing. So the process of setting up the test sequences and switching between tests then becomes very simple, as you'll see. And we can easily cater for automated limit checking, reporting and exporting of the measurement data, and importantly, for the first time, this is all available in the D-Scope Series 3 system with no automation scripting required. So, without further ado, let me get stuck into the practical measurements then. Let's get on to the interesting stuff and start measuring our amplifier. So I've launched the D-Scope Series 3 software here, and I'm going to click on my button here that says AutoSequence, which will launch this application here. And this is the AutoSequence host, which allows me to choose from any one of a number of sequences of audio tests that I've previously defined. I'm not going to take you through the detail of how you set this up. I'll save that for another day. But I have a sequence here called Part 1 of my Power Amplifier webinar. And I've got 4 tests. We'll cover the detail of these tests a little bit later on, but for now what I want to do is run these 4 tests so I can choose which ones I want to include in my sequence here. I'm going to do all of them. I've got a THD plus N test, THD plus N versus frequency, THD plus N versus power, and maximum output power versus frequency. So I hit my run all button. Now I could run all of these in an automated sequence as I am doing now. I could have loaded them and run them individually, as we'll do a little later when we get into the practical debugging. But what's happening at the moment is these tests are all executing, the results are appearing on screen, flashing in front of your eyes. Don't worry if you're not following what all the detail is here. We're going to look at that as we proceed through the discussion section today. But I just want to run you through these tests. So we're on THD plus N versus power now, the third of the 4 tests. And we've got red lights for the first 3 tests that have executed. That means that they have all failed. We would have got a green light if it was a pass. Unfortunately, it would appear that the first 3 tests have failed, and we're now on the 4th test, and there's a pretty good chance by the looks of things that this one is going to fail as well. So there we have it. Our test sequence has now failed, and if I really want to, I can now create a test report. This test report is going to be a fairly depressing reading, because in my report, well, my global result here, as we saw, was a fail. Test 1 THD plus N failed. Test 2 THD plus N versus frequency, that was a fail. Test 3 THD plus N versus power, that was a fail. Cool, this is depressing, isn't it? And the final test, maximum output power versus frequency, that failed as well. Well, that's not good news. And what I want to do is spend the rest of the discussion today looking at the reasons why those tests failed and performing some more detailed diagnostics on this particular power amplifier to try and get to grips with exactly what went wrong. So first of all then, let's take a look at the first test that we did, measuring our distortion result. Before we do that, I just want to give you a little bit of background. Let's just ask the question of our power amplifier measurements, what might we want to measure? We've seen a few tests already in that initial sequence, but let's just stop and consider what other metrics we might want to use when we're analysing our audio power amplifier. And there are many things. I've just taken a few examples here of some of the things that you might want to measure. Many of these are catered for in the Dscope Series 3 system, but I'm not going to do all of these today. That would make for a rather lengthy webinar. I want to focus in particular on distortion, and THD plus N is one of the distortion metrics that I'm going to look at today. Why the focus on this in particular? Well, I'm going to refer you to a diagram and a brief bit of text here from a gentleman called Douglas Self, who's written a book all about power amplifier design. And I'm not going to take you through a design workshop today. We're going to focus on the analysis, but I want to make at least passing reference to the fact that an amplifier, and this example here is a Class B amplifier, has many potential sources of distortion. And as a design engineer, one of the things that you're going to spend more time doing than anything else potentially is tracking down the various causes of distortion in your design to try and minimize them as far as possible. And again, without going into the detail, here are the 8 great distortion mechanisms according to Douglas Self, and all of these things could potentially contribute to your total harmonic distortion plus noise result, and any problems at any of these 8 stages could potentially give you issues. Let's just talk briefly then about THD plus N, this measurement that we're going to be looking at in some detail. Well, what is it, first of all? THD plus N. It is total harmonic distortion plus noise. And as I've shown with this slide here at the moment, the elements of harmonic distortion and noise have many different possible causes, contributing factors, and in short, THD plus N covers a multitude of sins, and it's fair to say that some of these distortion and noise products are potentially more objectionable, more audible than others, and the detail of that is perhaps a subject for another day, but the point that I'm trying to make here is that there are many things that could go wrong and could contribute to our THD plus N figure, and they don't all necessarily sound as bad as one another. So THD plus N is only a relatively weak correlating indicator of sound quality. We might need to use some more sophisticated tools to evaluate the performance of our amplifier, and also to try and figure out what's gone wrong if our measurements aren't as we expected. So let's return to the measurements then. Once again, just a quick reminder, this is the system that we're using here, DScope Series 3, connected to my computer that I'm presenting to you from, and we're measuring voltages across the dummy loads at the output of our power amplifier. So let me go back to the DScope Series 3 system then, and I'm going to load a slightly different test sequence which has a few more tests in it for diagnostic purposes. Let's load this second sequence here, and let me just switch this off actually. I don't want to use my spreadsheet mode at the moment, we can come back to that later. Let me start with the first test here. Okay, so this was the first test in the sequence that we ran earlier on, where everything failed. And what we're measuring at the moment is THD plus N, channel A, THD plus N, channel B, and this is a single tone measurement. So in my signal generator here, I have a sine wave. At the moment it's an amplitude of minus 10 dBu, frequency of 1 kHz, and my distortion, my harmonic distortion plus noise reading, is failing. Now, why is that? Well, let me ask you. I'm going to launch a survey now, and for those of you that are using a PC as opposed to a Mac, you will see a survey appear on your computer screens. And the survey says, why did this THD plus N test fail? And you have a number of options that I'd like you to consider, and select the reasons that you think this THD plus N test failed. For the benefit of those of you using a Mac who can't see these questions, the options are, this test could have failed perhaps. You think it's due to excessive low order distortion. Perhaps you think it's due to excessive high order distortion. Maybe there's some excessive broadband noise, the N component. Maybe you think there's too much main sum in the result. Maybe you think there's some other reason that we haven't listed. Or perhaps you just simply don't know. I'd like you to consider those possible answers, send your results in to me. The survey's anonymous, so we're not going to be embarrassing anybody. I just want to look at the statistics, and I'll give you a couple more seconds to consider those results, send your responses in, and we will now take a look at how you have all responded. So, let me now look at the survey results, and if we have any form of consensus here, it seems to be that we think that there might be an excessive amount of broadband noise causing my THD plus N test to fail. These are all possibilities, it has to be said, but in fairness, if we just look at the information that we're presented on the screen here, we really have no way of knowing what is the root cause of the problem here. If I want to understand why this THD plus N test has failed, I need some more detail. And for that, I'm going to load a different test from my sequence editor here. And in this test, I've got far greater levels of detail in the analysis here. So I've got some rather interesting and unique tools here that we refer to as smart FFTs, or FFT detectors more formally, and these are giving me lots of different numerical readings. How are they obtaining them? Well, they are in essence post-processing this spectral data here, my FFT that you can see here in red, which shows me the spectrum of the output of this power amplifier. So for example, in the top left hand side here I've got THD plus N. That was the reading that we had before, and it failed, so it's no surprise that it's still failing now. But I've got some additional measurements here that break open this THD plus N result into its constituent parts. So for a start then, I've got two readings here, THD and noise. So this is the THD and the N components of our total harmonic distortion plus noise result. The THD I've expanded into some finer detail here, so I've got the second harmonic, the third harmonic, the fourth, the fifth, the sixth, the seventh. I could have gone on if I chose to. I've even got a custom reading down here which allows you to program your own measurement functions. In this case I've chosen to calculate the ratio between the odd and the even harmonic distortion. So we've broken open the THD into a number of possible candidates, and we've also done the same for the noise. I've chosen to analyse a crosstalk measurement here, a mains hum measurement, and I'm also measuring some out-of-band noise as well. This is all totally configurable. This is just an arbitrary set of readings that I've chosen to set up for this test. But there's some very useful information in here. Now, we know that the THD plus N reading has failed. So was it noise or was it harmonic distortion? Well, we can see immediately from here that the total harmonic distortion reading is showing okay for the limits that I have set, but the noise reading is high. So that tells us that we're looking for a noise problem rather than a distortion problem. And if I just look along here to the right a little, we can see here that another of the readings that's in red is mains hum. And that suggests to me that there is a problem at 50 Hz or one of the harmonics. If we go to my FFT here, we can indeed see that there is a fairly pronounced amount of low frequency mains noise visible here. I'm in Europe, so this is a 50 Hz signal plus its harmonics there. Now this could be down to a number of possible issues. There could be a design problem with the power supply. There could be poor power supply rejection in the amplifier circuitry. We might have a ground loop in the measurement setup, for example. So not a problem with the device on the test in itself, but a problem in the way that we've wired up our device to the measurement system. I can actually reveal that the reason for this particular failure, the reason why my mains hum is reading high in this case, is because I have inadvertently misconfigured my test system here. And I've got an audio amplifier with unbalanced inputs, but I have set the test system up with balanced outputs. So there's no reference to ground at the signal generator output. Now if I switch to unbalanced, the 50 Hz signal drops significantly. And if I go back to my noise and mains hum readings, these are now looking okay. So I've solved that problem, but there still seems to be a problem here. What's this about? This is amplitude. Okay, that's showing me 17.6 milliwatts, which is saying low. Now, if I look at amplitude here, measured in a different unit, volts, that's reading okay. Right. Now, what you have to remember here is that your measurement system is fundamentally a voltmeter. It's a sophisticated voltmeter, but its native unit of measurement is the volt. And if you want to measure in units of power, as I am doing here, you need to tell the test system something about the external circuit. It can't know that you have an 8 ohm resistor or a 16 ohm resistor in the circuit if you just have a voltage probe. So what I need to do here is to go into my analyzer and, oh yes, look, I've got the default value of 600 ohms in here. If I change that to 8 ohms, watch what happens to the RMS reading here. 17.6 milliwatts at the moment. Change that to 8 ohms. Power equals V squared over R. R has changed, therefore so has power. And if I go back to page 1 now, everything looks okay. I can run my test to get my automated limit checking here, and yes, we have a green light now. The test has passed. So we've solved the two problems there. In this case, it was actually operator error. We had misconfigured our measurements, and that was the reason why that particular test had failed. Okay, so let's move the discussion on then. Let's go back to the slideshow, and we're now going to talk about some sweep measurements. We saw a couple of sweeps in our initial sequence where everything failed. We're now going to come back to some of those measurements and take a closer look at what happened and why. So just a reminder once again, this is how we have everything set up. I haven't changed anything. This is the same setup that we've used throughout. So we'll jump back into the test system and take a look at these sweep measurements. Okay, so the test that we had before was total harmonic distortion plus noise versus frequency. Let's load that test. And this was the result that we had. This is what we saw in our report earlier. So I've got a limit line on this sweep, this orange line here on the trace, and my channel A and B distortion readings were okay at low frequency, but at high frequencies they started to breach this limit line. So this is a sweep. What I did was I measured my THD plus N result for channel A and for channel B. I could have chosen some more, but not in this case. And the variable that I was adjusting for this sweep was the signal generator frequency. So we started at 20 kHz, stopped at 20 Hz, and we chose 20 points along the way. And that was my result. So, well, what went wrong there then? Again, let me ask you, the audience, what you think the problem was there. So I'll launch the next survey question, and that survey appears to have come to an abrupt end, so I just need to reload that. Okay, let's try that one again. Start the survey. Okay, so again, for those of you using a PC rather than a Mac, you will now see this survey on your screens. Why do you think this THD plus N versus frequency test failed? And you may think that we had excessive amplifier noise at high frequency. Maybe we had a rising distortion response at high frequency. Perhaps I used the wrong waveform for the test. Maybe I had the wrong filter settings set up. Or the wrong signal amplitude, perhaps. Or maybe you're just not sure. You don't know what the cause of the problem was there. Again, I'd appreciate your honesty. If you could tell me what you think went wrong with that original test, I'll be grateful. And we will look at how you responded in just a moment. Alright, so let's do that. I'll give you 2 more seconds to finish up, so if you're going to click the buttons, please do so, and we will now stop that survey. Okay, good. So you were fast on the buttons there. I'm grateful for that. This is how you have responded. And some of you think there was rising noise at high frequency. Some of you think we had high distortion at high frequency. Maybe I used the wrong waveform. Let's take a look. I don't really know what the answer is, actually. Again, having looked at these results here, all it really tells us is that the THD plus N result failed. And the best way of establishing why that failed is to take a more detailed look at the analysis. So I'm going to load a slightly different file once again. And in this case, in addition to the THD plus N result that we had before, I'm also going to include THD, so just the harmonic distortion without the noise, and the second harmonic, and the third harmonic as individual results in my sweep here. So once again, I'll adjust the generator frequency as part of this sweep, and I can now run this particular test. So what we'll do is we'll start at high frequency, sweep down to low frequency, and the results that you see on the screen, the red trace is THD plus N, the yellow trace is THD, the green trace is second harmonic, and the blue trace is third harmonic. Now, I seem to have taken one problem and created another. I've now got some additional test failures here, and that's confusing me because I'm seeing that the THD plus N result in red is a pass, but the individual harmonics, the second and the third, and also the THD measurement have all failed, which is very confusing because my total harmonic distortion plus noise test didn't fail, so why should the others fail? Well, let me put that question to one side for a moment. Let me deal with the easier one first. So let's just consider our high frequency result here. Well, we can see that in the red trace, the THD plus N breaches our limit line at high frequencies, and the yellow trace, which is THD only, so without the noise, essentially follows the same line. So the THD plus N looks like it is dominated by harmonic distortion. So that's telling us that this isn't a noise issue. We do indeed have a rising distortion response at high frequencies. But let's just stop and think what we're trying to measure here. More often than not, not always, but more often than not, what we're trying to quantify is the audible distortion from our power amplifier, because that's what matters most. It's not the only thing that matters, but generally speaking, it's the audible distortion and noise that we're primarily concerned with. So we have a question as to what bandwidth we want to measure over. And if I go into my settings page here, you can see that for all my results, THD plus N, THD, second harmonic, third harmonic, I have a high pass filter, which means that I'm not measuring anything below 20 Hz. but my low pass filter is off. So we're measuring the harmonics up to, in this case, about 96 kilohertz, which goes well beyond the normally accepted audible range. What I might want to do is really, for my data sheet, the number that I quote to my customers perhaps, is constrain this number to the audible bandwidth of 22 kilohertz. And if I do that, go back to my sweep again, let's rerun it, see what happens. There we have it. The audible distortion is now actually below this limit that I imposed on my measurement here. So my result is now what I expected. I've set the filter to the intended setting that covers just the audible components. But I'm still left with this additional problem at low frequency, where I have this rather curious result that shows me that the THD plus N reading is within limits in red, but the THD reading, so we take the noise away from the result and it breaches the limit. So what is happening there? That seems very odd. And we also have the fact that the second harmonic and the third harmonic also have breached that limit. And these are all plotted on the same scale, by the way. So what happened there? Well, the issue here actually is that I'm using some sophisticated FFT-based analysis tools that rely on some rather interesting filters. Let me just explain. If I show you my FFT trace here, there it is. There's my signal at 1 kilohertz that you can see clearly on the screen there. I'm measuring THD plus N, I'll just change the colour of this filter actually, using this white filter. So it's just a band reject filter that takes away the 1 kilohertz tone and allows us to analyse the residual, the remainder after that filter has been applied. THD, well, that's being measured by this bank of ideal brick wall notch filters. So we're just analysing the individual harmonics and nothing else. Second harmonic and third harmonic in green and blue likewise are again just ideal brick wall notch filters. Now everything looks fine at the moment, but then everything looked fine on my trace at 1 kilohertz. It was really below about 200 or 300 hertz where the problem started. So let me go down all the way to 20 hertz in my signal generator here. Now that's a clue. That's showing us that the fundamental here in red at 20 hertz is basically leaking into the filter bandwidth of this THD measurement filter. And we also can't discriminate any of the individual harmonics in this filter anymore. This looks to me like it's a resolution problem. We're looking on a logarithmic scale here, and an FFT is plotted with equal spacing on a linear scale between data points. So what this says to me is that I've probably got an inappropriate FFT size here. Let's try a bigger one. Well, let's go up to 64K. Okay, we've got a bit more resolution, but that doesn't seem to solve the problem. Let's just go all the way to the biggest setting here, 256K. I have to wait a little while. This takes a long time, even just to acquire the audio data. But that solves the problem. We are now able to discriminate these individual harmonics as distinct entities from the fundamentals. So that was the explanation. So let me, well, I could run this sweep at this FFT size, 256K, but you can see that even just one FFT is taking the amount of time that this red bar takes to update at the bottom of the screen. So this isn't the fastest approach here. And I don't need large FFT sizes at high frequencies, as we've already seen. So let's reset this back to something small. Let's go back to 1K where it's all fine. What I want to do is to run a sweep that gives me the best of both worlds. I want to have a small FFT size at high frequency where I don't need the resolution but I would like the speed, but I want to use a large FFT size at low frequency where I have to in order to obtain the required resolution. So what I'm going to do is turn on this clever little script here, adaptive FFT size. This will fire on every sweep step and it will select the most appropriate FFT size to give me the best trade-off between measurement speed and resolution. So if I now do that, having catered for this low frequency resolution problem, rerun my sweep. We've already dealt with the high frequency issue here. Turn those filters on. And now at low frequency, well, we can see that the sweep is slowing down a little. This is now switching in progressively larger FFT sizes, which are taking longer to execute as this sweep nears the low frequency end. And this sweep is now just about to finish, and well, that's a relief. I've now found all of the problems. This test has now gone green, it has passed, and I've identified what the problems were in my initial analysis. Great, so let me now move on to the next test that we looked at. And one of the measurements that we had was THD plus N versus power. This was one of the tests that we ran in the initial sequence. Like all the other tests, it failed, and now we want to know why. So what we've got here is, on the x-axis we have the output power of the amplifier plotted here. So we've got 1 milliwatt on the left hand side, we've got about 100 watts on the right hand side, and these are the measured curves of my output power, maximum output power. This is the distortion versus the output power, the total harmonic distortion plus noise versus output power. And we can see at the low amplitude end of the scale, where the power output is low, we have breached my measurement limit. And once again, I'd like to know why that is. So let me again ask you, the audience. I will launch another survey question, and this survey will ask you why you think this particular measurement, THD plus N versus output power, failed. Is it due to a rising noise floor at low power, low amplitude? Maybe you think it's down to rising distortion at low amplitude. Perhaps I used the wrong signal frequency for this test. Or maybe it was down to the way that the THD plus N result was calculated. Maybe there's some other reason that explains this result. Or perhaps you just don't know. Again, I'd be grateful if you could complete the survey as honestly as possible. Let me know what you think went wrong, and we will then do a little bit more digging to see if we can get to the answer to that question. So I'll bring that survey to a close and show you how you responded. Okay, so more of you than any other option have chosen the answer, the first one, that you think that this was due to rising noise floor at low amplitude. That was one of the possible options. Some of you think it was due to rising distortion. Some of you think I had the wrong signal frequency. Interestingly, 8 of you think that this is down to the way that the THD plus N calculation is actually performed. Well, let me do a bit more detailed analysis, and hopefully we'll find out which of you were right in that particular survey. And there's no real criticism here. We don't actually really have enough information here to tell us what was happening. You might have an idea about what's happening if you've done this type of test before, but for the purposes of those of you who are less familiar with this particular type of test, let's load something with a bit more detail here, and we can probably get to the bottom of the problem. So I've loaded a variant on that last sweep where, instead of just looking at THD plus N, I've got that result again still here, THD plus N, but I've also got THD only, so total harmonic distortion without the noise, and I have the noise isolated as a separate result as well. And I've thrown in the third harmonic. The reason for that really is that the THD tends to be dominated by third harmonic distortion when we're talking about the onset of clipping. So as you approach the maximum output of the amplifier, you tend to see clipping distortion, which is dominated by the odd order components. A little bit more on that a little later. For now, let's just explain. Okay, so we were sweeping, this time not the generator frequency, but the generator amplitude. So we were increasing the amplitude of the generator, which increased the output of the power amplifier. Therefore, the measured power was increasing as this sweep executed. Alright, so let me run this slightly more detailed diagnostic version of the test. I'll hit the run button here, and I'll just talk you through the results here. The THD plus N result that we saw before, that's shown in red on the trace. The THD only, so just the total harmonic distortion, that is shown in yellow. The third harmonic is shown in green, and the noise here is shown in blue. Now, we know that the total harmonic distortion plus noise failed, at low amplitudes. So our prime suspects for our initial contenders for the problem would be possibly total harmonic distortion or noise. That would seem to be a reasonable assumption. However, if I look at my total harmonic distortion measurement, so this is THD only, no noise, in the yellow trace here, this is broadly flat at low amplitudes, and it's certainly below the limits that I've imposed on this test here. So THD is not the problem. This amplifier, okay, there's a modest rise in distortion at low amplitude, possibly due to the effect of crossover distortion becoming more significant at low amplitudes, but it's not the reason for the failure in the test. If I now look at the noise measurement, this doesn't look like a contender either. This is showing me that the noise seems to be broadly constant at low amplitudes. And when you think about it, that's probably what you would expect. You would expect that the noise at the output terminals of your amplifier was independent of the signal amplitude, in most cases anyway. Now, one thing to notice here is that I've plotted noise on an absolute scale here, so dBu. That's an absolute measurement unit, and that shows us, as we've said, that the noise measured in absolute terms is flat. So what is going on then? We've seen that the THD isn't responsible for this measurement failure, and we've seen that the noise isn't responsible for this measurement failure. So what was it? Well, I can reveal that 8 of you were correct, and you did identify the problem, and that is that when we calculate THD plus N, the most common way of expressing this is in self-relative dimensionless units. So quite commonly either dB or percentage are the main units that you would use to measure THD plus N. What does that mean? Well, the fact that it's self-relative is telling us that we're calculating the distortion and noise energy as a ratio of the signal amplitude. So we're comparing the amplitude of the signal with the residual noise and distortion. And when we look at the low amplitude end of this sweep here, what's happening is that the distortion in relative terms is reasonably flat. The noise in absolute terms is flat, but because we're getting down to low amplitudes, the noise is starting to dominate the THD plus N result, and as a proportion of the total signal energy, the THD plus N is rising because the signal amplitude is dropping at the same time as the noise is staying constant in absolute terms. So this is really a consequence of the way that we're doing the measurement, and we have to be very careful about interpreting measurements like this, which is THD plus N versus output power. This is not necessarily telling us that we have rising distortion or rising noise at low amplitude, and as we have identified in our measurements here, we don't have either. We don't have rising noise and we don't have rising distortion. So what we can do, and this might be a more appropriate test, is we can plot just simply THD, so total harmonic distortion without the noise, versus output power, and this perhaps gives us a slightly more realistic view of what's happening from the point of view of distortion in this particular device. And then if we wanted to, we could isolate the noise as a separate quantity, either in absolute or self-relative terms. So when we measure it in this way, as I've just shown you, we do indeed get a test pass. That's a relief. The amplifier isn't broken. It was really just a consequence of me misinterpreting the measurement that I had configured. So an important lesson there that hopefully I've made clear for you. Alright, let's go back to the slideshow then, and let's talk about maximum output power. That's probably one of the things that you would want to measure fairly early on in your analysis of your amplifier to make sure you've hit your target output power performance. And I said I was going to talk a lot about distortion and THD plus N today. Well, that is all tied into how we evaluate the maximum output power of our amplifier. We need a way of knowing when we've hit the maximum output, and we actually use distortion, harmonic distortion plus noise, as a means of determining that we have reached the maximum output power. Okay, there are a few different ways of measuring output power in terms of the duration of the test. We have continuous output power, which is taken as being a continuous sine wave, usually of a relatively short duration. You just set up your sine wave, make your measurement and say, yep, that's my output power. But you might want to measure over a very short duration burst period to evaluate how the amplifier behaves in the presence of short dynamic swings in the audio signal that it's being asked to reproduce. So that's a slightly different result. And you might also be concerned with the long-term output power capabilities of your amplifier. So in other words, its ability to sustain a high-level signal for an extended duration of time, perhaps a minute, perhaps 10 minutes, maybe an hour or 24 hours, depending on the standard that you're actually working to. So let's look at these in turn then. Let's first of all consider the continuous output power case. That's the one that we looked at earlier in our initial sequence where all of our tests sadly failed. And this is what we were doing. So once again, we had the same measurement system here. I've just shown one channel for clarity. And we've got our device under test amplifier driving current into an 8 ohm resistive load, measuring across that load, across the amplifier terminals. But what we were doing in this test was we were adjusting automatically the generator amplitude such that we were seeking out the point where the amplifier hits its limit, and that is defined as the clipping point. So when the amplifier starts to turn our sine wave into a square wave by virtue of its output voltage limiting, we start to see an increase, a rapid increase in THD plus N, which is exactly what we saw in the previous sweep actually. Now, depending on the standard that you're working to, the definition of the maximum output power may be stated as the point where you hit 1% THD plus N. Some high-fidelity manufacturers use 0.1% as their definition of the onset of clipping, and some manufacturers, particularly in the consumer market, use a standard that states that 10% is the definition of the onset of clipping. The reality is that although those different numbers will give you different output power ratings, and generally speaking, the higher the distortion level, the more output power you will have, it doesn't really matter which one of those standards you use, provided that you use the same one for making comparative measurements of different devices. So just for the sake of argument, I'm using 1%. I'm sitting on the fence right in the middle of those three options, and I'm going to use 1% as my definition of the onset of clipping for today's demonstration here. So let's go back to the measurement then, and let's recall the test that we ran earlier. And this is what we saw. We saw that we had broadly constant output power with respect to frequency, but at high frequency this measurement breached its limit. So we had a higher output power measurement at high frequencies than we did across the rest of the audio band. Now that's a bit of an odd result, isn't it? You would probably expect that the amplifier would have a maximum output power rating that was broadly flat with respect to frequency. I certainly would expect that. I think that's a rather odd result, so let's see what you think the explanation is. So, once again, another survey will appear on your screens for those of you using a PC rather than a Mac. Apologies to Mac users, I'll read out the survey for your benefit. So why did this output power versus frequency test fail? Perhaps it was because the amplifier power output genuinely does increase at high frequencies. That's one possible explanation. Maybe the output power decreases at high frequencies. Maybe the amplifier distortion increases at high frequency. Or perhaps I've used the wrong measurement filter somewhere in this particular test. Maybe there's another explanation. Or another option here, maybe you just don't know what the answer is at all. So again, I'd be grateful if you could complete your surveys as quickly as possible to give us a chance to get on and look into this particular issue in a bit more detail. So why did this amplifier appear to give us more output power at high frequencies than low frequencies? Let's take a look at the responses. Okay, so the majority of you thought that either the amplifier distortion increases at high frequency or the wrong measurement filter was used for this test? Well, we saw in an earlier measurement that yes, the amplifier distortion did increase at high frequency, but if that were the case, we might expect to see the output power decrease at high frequency. So maybe it was the wrong measurement filter then. Well, let's consider that question in a bit more detail. So what we're measuring at the moment, remember, we're measuring THD plus N, so total harmonic distortion plus noise, and we are, in this test, starting at low frequency, moving up to high frequency, and at every frequency in this sweep, I have a checkbox here checked saying that we want to regulate at every sweep step. What does that mean? Well, what it means is that we are running an algorithm here to automatically seek out the point where this reading, THD plus N, reaches our value of 1%. So that was my definition of the onset of clipping. As I say, I could have chosen a smaller number or a larger number. I'm choosing to work to this particular standard, which is 1% as my definition of clipping. In this regulation then, the instrument is automatically adjusting the generator amplitude, ramping it up and down, seeking out the precise point at which the total harmonic distortion plus noise reaches 1%. And we do that at a range of frequencies. So let's just stop and think about what might be happening. Now let's go back to the settings for this THD plus N instrument here. So we've currently got THD plus N loaded as our measurement function, and we talked earlier about the fact that it might be a good idea to constrain your measurement bandwidth to the audible range, 20 Hz to 20 kHz approximately. So that's what I did for this test. I thought that was a sensible thing to do. However, what we're doing here is at high frequencies. Let's take, for example, 15 kHz. At 15 kHz, all of the distortion energy, second harmonic, third harmonic, and everything else, occurs from 30 kHz and upwards. So in this case, that's beyond the upper limit of my measurement filter here. So in other words, I might be at the onset of clipping, but I've filtered out those harmonics from my measurement, and therefore the distortion appears to be lower than perhaps I might want to measure for a clipping test, and therefore I need to ramp the generator amplitude up further in order to hit my 1% THD plus N figure. So in this particular test, it may be argued that it's a bad idea to have a low-pass filter engaged on your THD plus N measurement if you're interested in looking at the onset of clipping. And if I now run this test again with that filter off, let's do just that. Here we go. So this is now running a regulation. You can see that the generator here is automatically ramping up and down, and that's causing a corresponding change to this THD plus N reading. I'm not touching anything here. This is happening automatically. You can see that the sweep is executing, so we're switching through a range of different frequencies here. We're now up to the 10 kHz measurement, and that is much more like what I would expect to see, a much flatter response here, where we appear to have broadly consistent output power at all of the frequencies that we've tested at. So again, that's a relief. I found out what the problem was there, and it's important that you stop and consider what you're measuring and how, and what filters might be being applied to your tests, in order that you ensure that you set them up to give you the answer that you're expecting. The test instrument will give you the result that you've set up, but you need to stop and think about what it is that you're attempting to accomplish before you set the instrument up. Alright, well, we're making some progress, aren't we? We've now managed to get all of those tests that originally failed to pass. We've got green lights throughout. So let's go back to the slides now and look at what we're going to talk about next. Well, I wanted to talk in a bit more detail about maximum output power and consider both burst output and long-term output power before we move on to revisit the other tests that failed. So, burst output power then. What do we mean by that? Well, we've got to be a little bit more careful here. For a start, when we look at our measurement in a second, we will see that we need to set up a burst stimulus in our signal generator. So we need a very short duration burst, usually of a sinusoidal tone, which again allows us to be analytical about the types of distortion components that we might want to measure. And we need a way of calculating short-term power. So we need to be very specific about where we start and finish our measurement, because we want to be measuring this during the high amplitude, short duration part of our burst. And likewise, when we evaluate the distortion, which again can be used to define the onset of clipping, we need to be able to evaluate distortion over a short period of time. So let's look at how we might go about doing just that. So I'll go back to my sequence editor here. I'm going to load my burst power test, and I'll just briefly talk you through what's happening here. But let me start with the audio signal itself. Let's look at the time domain trace here, and I'm just going to expand this so you can see the signal, and let's zoom all the way out in the x-axis. There you go. So that's our audio signal. It's a burst, as we have defined here in our signal generator. The amplitude is currently set to -20 dBu for the high part of the burst, and the low part is offset by 40 dB in this case, 40 dB lower. For the on part of the burst, I've got a 20 millisecond high level signal, and then a 480 millisecond low level signal. And that gives us the waveform here in green. But I need to be careful about where I analyse this signal, and I'm using this blue window here to just incorporate this part of the measurement in my subsequent FFT analysis. So again, if I zoom all the way out, you can see that this window is just applying to this part of the signal. That's the only part that we're going to actually analyse, to ensure that we're just looking at the amplitude and distortion of the high part of our burst. Alright, so the next part of the analysis here, we're measuring total harmonic distortion, and this is a user-defined algorithm here. We've got a bunch of standard analysis algorithms that you can choose from. You can expand this list, or you can even create your own analysis functions here. So we're calculating the total harmonic distortion over just the period of this short burst here. That's what this particular algorithm is calculating for us. And again, we've got another user-defined analysis algorithm here, and this is calculating the RMS amplitude in volts and then converting that to an equivalent continuous power over this short period. Okay, so what was happening in this test was that we were again using a regulation. So here is our regulation on this second page of the configuration to seek out the 1% clipping point of that short duration THD measurement by adjusting the generator amplitude automatically. So now when I run this test, you will see the waveform here is being adjusted up and down incrementally. The harmonic distortion has now breached the 1% limit, so we've got to ramp back down slightly. You can see the levels changing up here in the signal generator as we're seeking out the 1% total harmonic distortion point, and that has now been found, and we have now confirmed that the output power at the full-scale output for a burst signal is now 20 watts. And we'll take a look a little later at the test report, but that's actually a bit higher than it was for our continuous output power test. So that shows us that the amplifier has a little bit of headroom for dealing with short duration dynamic bursts in our audio signal. Okay, so let's leave that one there for a second and come back to the slides, and let's just see what we're going to talk about in this final part of the maximum output power discussion. We're now going to talk about long-term output power. So this is a measure of the amplifier's ability to sustain a particular level of output for an extended duration of time. Now this one's quite a tricky test as well, potentially. What we're concerned with here is what happens to the amplifier over an extended period of time, and the ideal scenario, of course, is that we come back to our amplifier and we don't find a smouldering heap of semiconductors. That would be a bad result. What we want to find is an amplifier, ideally, that's still working. But more than that, we also want to know whether the amplifier worked flawlessly throughout the test, or whether perhaps some form of thermal protection may have engaged mid-test. So this helps us to determine whether the amplifier has been designed correctly, so we've got the heatsink calculations correct if we've determined that a heatsink is needed, and it tells us whether the thing has been built correctly and the output devices have been thermally coupled to their heatsinks correctly if heatsinks are present. So this is a reliability test, which is rather different to just a continuous output power test. Now what might happen is that this sort of scenario could occur. We've got a constant output power from our power amplifier as it sits there on the bench, and it slowly warms up as the output devices and possibly the heatsinks too start to warm up. And what might happen is if this thing gets too hot because we haven't designed it properly or there's a fault with it, well, it may blow up. That's one scenario, and we'll certainly know if that has happened when we come back at the end of the test. But it may be that this device is sophisticated enough to mute or to lower the gain when the output devices get too hot. So we might see this sort of scenario where the power is reduced or falls to zero for a period of time. Perhaps the amplifier then cools down and recovers. What happens if we analyse the amplifier here? So if we come back after 24 hours or 10 hours or whatever our test period happens to be, and we put our test system probes on the output of the device, it will look like nothing has gone wrong if we measure at this point in time during the test. And of course something did go wrong, but we weren't looking at the time. So we need a way of picking this kind of problem up. And you could get a sophisticated data logger to help you here. You might want to employ all sorts of safety precautions to make sure that your amplifier doesn't start a fire when you go home after starting this test off. But what we can do here, and I'll show you this now, is to actually run a long-term output test from the DScope Series 3 system without having to invoke any external data logging equipment or anything like that. So what I'm doing here is I'm monitoring my output power. This is currently running at about 1/3 rated output power, just under 7 watts in this case, and I'm monitoring the THD+N. I could set up another reading here for the gain or whatever else I wanted to test. And what these readings will do is these will illuminate red if the test limits are breached at any point. So let's just pretend that the amplifier's got too hot and it's going to attenuate the signal. The gain has been reduced to save the amplifier from going up in a big cloud of smoke. Okay, so we can see the readings here. They've gone red. That tells us that the test has failed. But if we reset this test condition, this fault condition rather, reset the amplifier back to full gain because it's now cooled down, if we were to just look at these numerical readings or the trace window or any other type of short-term analysis, we would not see a problem. But crucially, I've got a log here, an event log showing me all the events that happened since this test was launched. And this is a soft log. This is basically a file on my computer that will run indefinitely, recording all of the results until I stop the test, or perhaps if I've got a really bad problem, my hard drive fills up. But that would be a big problem. So this logs the date and the time and the event that happened, tells me what limits were breached, and this can be applied to all sorts of different measurements. My event manager here basically allows me to set up all manner of different fault conditions and reading panel limit checks and so on. I've just used a couple of them in this test, but that was good enough for me. That showed me that this amplifier, despite now appearing to be working okay, did fail my tests on a number of occasions, and it shows me that something has gone wrong. And I've then got an idea of when those problems occurred, how long they occurred for, and that should help me go back and re-engineer or adjust my amplifier design. Okay then, so finally we've talked a little bit about blowing up amplifiers already. Let's just stop and think about other ways that we might potentially cause some catastrophic damage on our bench, which is of course something we'd all rather avoid if we can do. It's expensive and it's time consuming, but it does happen. I know from first-hand experience that things can go pop on the bench, and we don't really want that. So let's just consider a couple of things then. First of all, one question you do need to ask yourself is related to your test instrument inputs. And specifically, this is a question for people who are working with bridge-tied amplifier designs. And the question you need to ask yourself is, does your test instrument have a single-ended or a differential input? What do we mean by bridge-tied amplifiers? Well, this is the kind of thing we're talking about. This is just taken from a standard off-the-shelf part. A bridge-tied amplifier, rather than having one terminal that is essentially a ground connection and another terminal whose voltage swings either side of that, in the bridge-tied case we have two live terminals that are effectively operating in push-pull, both swinging either side of a nominal midpoint. So in other words, if you were to take perhaps an oscilloscope probe that was mains grounded on the ground input and connect that to this particular amplifier, you would be in trouble basically. You would be shorting out one of the output terminals. If the amplifier is smart enough, it may just shut down or mute. If it's not, then you may see that rather unfortunate pile of smoking semiconductors that we were hoping to avoid. So, ask yourself the question, before you connect anything, does your test instrument have a single-ended or a differential input? In the case of an oscilloscope, there's a good chance if you have a two-channel scope that even if it is single-ended, ground-referenced, you may be able to use two probes in tandem and set them up in differential mode. But remember to do that before you connect the probes. In the case of the system we're looking at today, the D-Scope Series 3 measurement system, well, this has the facility to allow you to connect a bridge-tied load type device directly to the 2-pin input terminal, the BNC input terminals at the analyzer. The reason being that our what might appear to be a single-ended input, the BNC, is actually connected between pins 2 and 3 of our differential XLR input. So, in other words, the BNC inputs operate differentially by default. There may be situations where you want to use a ground-referenced unbalanced input, in which case we have this red adapter here that plugs into the instrument, but don't plug it in if your amplifier is a bridge-tied load design. Okay, so that's something to consider at the measurement instrument input. And another issue that potentially could cause you problems is amplifiers with very high output voltages. Now, there's a range of measurement equipment out there that you could use to test your amplifiers with. It will inevitably have some upper limit on the maximum voltage that it can safely handle. In the case of the D-Scope Series 3 system that we're using today for our practical demonstrations, it can handle a maximum input voltage of 159 volts. So what that means in terms of amplifier power depends on, of course, the load impedance that your amplifier is driving current into. D-Scope's limitation is a voltage limitation. So if your device is capable of outputting 159 volts, or rather more than 159 volts, then it's a pretty good idea not to connect it to the input terminals directly. And likewise, you should check the maximum input ratings of whatever test system you're using before you connect an amplifier to it. If your amplifier output does exceed the maximum input of your test system, it's not a major problem. You can potentially use attenuators in the circuit to reduce the voltage that is presented to the measurement system inputs. However, that does then mean that you need to get your pocket calculator or your telephone or your computer calculator app out to calculate the equivalent voltages and powers that are actually present at the amplifier output rather than at the test system input. Thankfully, in the system that we're using today, we have a neat little feature here that allows us to automatically compensate for any positive or negative external gain in our measurement circuit. So if you're using a preamplifier for a microphone, for example, you can put in a positive gain corresponding to the mic pre-gain. If you're using an attenuator circuit, as we would be doing in this power amplifier scenario potentially, we can dial in a negative gain that corresponds to the amount of attenuation presented by the network that we've built. And that allows us to measure voltages that are in excess of the test system's input by measuring indirectly after an attenuator and compensating for that attenuation so that the voltages and powers that we measure are equivalent to what would have been present across the terminals of the amplifier under test. So just to explain this in diagrammatical form then, rather than just in words, again, here is my test system with my amplifier driving current into an 8 ohm resistive load, but I have an additional attenuation network in parallel with that load. So my amplifier is driven by the test system generator as normal, but I take my feed to the analyzer input from across the attenuation network rather than across the output terminals of the amplifier. So just a quick example to see this in action then. I'll jump back to my test system and I'll load this final test here, this high output level test. Now, because I'm dealing with high output levels here, there is potentially a safety issue to consider. So in this test, I've deliberately turned my signal generator off so that if I've loaded this test and connected my amplifier, if I'm making any connections manually, I'm not going to risk causing any damage to myself, which is of course another consideration. Avoiding destruction of oneself is certainly desirable. This test will only turn the generator on when I hit run. So if I now hit run, the generator turns on, and once the test has completed, the generator now turns off again. Well, this test has failed. My readings were red. You may not have had a chance to see what the voltages and powers were, but what I can tell you is that I didn't dial in my attenuator gain here, so I had minus 20 dB in that attenuator. If I now rerun this test, there we go. So the test has now passed because I've correctly compensated for that external network there. So now, if I hit my test report here, I've now got a comprehensive report of all these tests that I've now run, and these are slightly more detailed, as we saw. We've gone through some more in-depth diagnostics to get to the bottom of why our original tests failed. And there we have it. We've got a graphical and numerical report of all the tests that we have now conducted, and thankfully, that's a relief. All my tests have passed, and I'm now able to move on and design my next amazing power amplifier circuit. So, having debugged all of those tests then, let's go back to our presentation here and just quickly recap some of the things that we've talked about. So we've seen a lot of measurements today using THD plus N, total harmonic distortion plus noise, as their foundation. Very widely used on manufacturers' data sheets, on product information guides that are supplied to end users. It's a great starting point. It's great for having a consistent, well understood measurement that most of the audio industry uses. But when we're talking about benchtop analysis, we more often than not need some more in-depth analysis to get to the bottom of why our tests have failed if our readings are higher or perhaps lower than we're expecting. Lower is generally not a problem, but in some cases it may be. And we've seen some examples of using highly selective measurement methods involving FFT-based analysis that can really help us get to the bottom of what might be going wrong, either in our amplifier design or perhaps in the way that we've set up our tests, which we've seen a number of examples of today. We've seen several ways of measuring the output power of our amplifier, and a quick note here, it's important to clarify when you're talking about maximum output power, are you talking about the burst output, are you talking about the continuous output, or are you talking about the long-term output? And we've seen a couple of examples of the perhaps slightly non-standard power output measurements, so burst outputs and long-term output power. We need some reasonably sophisticated tools to allow us to perform that kind of analysis, which goes beyond just your conventional continuous output power measurements. Now, we should stop and deal with the question of what happens when you measure an amplifier on different test systems. This is something that we sometimes run into, people getting different answers on different pieces of measurement equipment and scratching their heads asking, well, what on earth is going on? Well, I've only shown you examples with one measurement system today, but I've shown you that there are potentially quite a lot of different settings, lots of fine detail to consider when you're setting up your amplifier measurements. Fundamentally, the instrument that you're using is a voltmeter, and it will give you the same answer as a different voltmeter, a different audio measurement system, provided you have them both set up in the same way. And of course there are a number of places you could fall over along the way getting your test system set up consistently, and we've looked at just some of them today. So hopefully this has given you a much better idea of the kind of things that can and sometimes do go wrong, and where you need to look out for these types of problems when you're making measurements on your amplifiers. So one of the most important lessons out of all of this is to know your instrument. Know its characteristics, its input voltage limitations. You should get to know the schematics of the inputs and outputs if they're provided, or at least a high-level architectural diagram if that's provided, so that you can understand what it is that you're measuring and how to connect your test system to your device, which may or may not be trivial. Alright, so some topics that we've not had a chance to cover in detail here today. We didn't really look at a huge range of measurements here today. We concentrated on distortion and output power. There are, as we saw earlier, many other types of results that we might want to measure on our amplifier. We might want to talk about high-speed measurements like multitones, for example. We haven't really talked about high-speed automated testing, perhaps automating your measurement system for an external automation executive. We haven't really paid any attention at all to Class D amplifiers. We haven't talked about digital interfaces, which are of course more common than ever before on all sorts of audio devices, including amplifiers. And sadly, we don't have time to cover these things today. By all means, you can raise some of these issues in the Q&A, but these types of topics for further consideration have been dealt with, to some degree at least, in some cases very extensively, in our previous webinar program. So I'll ask my colleague Bernhard Nocker to post this URL into the NetViewer chat panel. You're more than welcome to browse the Prism Sound website to look at our volume of past webinars that are available to download or view on demand. Please do take a look at those. They are a useful resource for this type of additional material. A couple of quick references then. I showed you a couple of excerpts from a power amplifier design book by Douglas Self. That's available on your favourite online bookstore, and there's just one example on the screen there. And for those of you using the Dscope Series 3 system, the first beta release of Auto Sequence is now available on our website to download. This will shortly be updated to a later beta version, and after that it will be absorbed into the standard product, so you won't have to download and install this additional application. So thank you all for your attention. I hope you found today's session informative and interesting. I'd look forward to seeing as many of you as possible on a future Prism Sound webinar, and I'd like to thank my co-presenter here today, Bernhard Nocker, for keeping on top of the co-moderation role through the presentation. But yeah, from us for now at Prism Sound here at the UK headquarters, I'd like to say one final thank you to you, the audience, and we'll bid you farewell for now. So thank you and goodbye.